Welcome to Lecture 3 of the RadSound Basic Radiation Physics Masterclass. Today, we're getting our hands dirty and talking all about the gadgets. And that is the absolute truth, isn't it? You cannot protect what you cannot measure. Every single radiation measurement, whether it's calibrating a CT scanner or just looking for a lost radioactive source, starts with one of these detectors. So let's get into it.
So here's our game plan. We're going to go on a little tour of the essential hardware. First, we'll cover the basic physics behind it all. Then, we'll meet the three big families of detectors: the classic gas-filled tubes, the amazing glowing crystals, and the super high-tech solid-state sensors. And then we'll wrap up by figuring out how to pick the right tool for the right job. Okay, so in our last explainer, we talked all about the quantities, right? The grays, the sieverts, the becquerels. Well, now we're going to look at the actual instruments that give us those numbers. How do we take something totally invisible, like radiation, and turn it into a signal we can actually read?
Well, believe it or not, every single detector we're going to talk about today boils down to one of these three fundamental physical principles. You either knock an electron off an atom in a gas, you make a special crystal flash with light, or you create a charge signal directly inside a solid. That is it. Every single gadget, from a simple survey meter all the way up to a cutting-edge CT scanner, starts right here.
Let's kick things off with the oldest and, honestly, the most straightforward family. At their heart, these are really just a box of air with a voltage. You've got a sealed volume of gas, like air or maybe argon, with two electrodes inside. Radiation comes in, it creates charged ion pairs, and the voltage you apply pulls those charges apart, creating a tiny electrical current. The real magic, and what separates one type from another, is just how high you decide to crank up that voltage.
And this curve shows that journey perfectly. If the voltage is too low in that recombination region, the ions just find each other again and poof, no signal, useless. Turn it up a bit and you hit this beautiful flat plateau, the ionation or saturation region. Here you collect every single ion pair the radiation creates. It's perfect for precise measurement. Now crank the voltage even higher and things get interesting. You hit the proportional region. Here, the electrons get so much energy they start causing more ionizations themselves, amplifying the signal. And what's cool is the amplification is proportional to the initial energy. But if you turn the voltage way, way up, you get to the Geiger-Miller region, where just one event triggers a complete avalanche.
So, the most important thing to remember is that ionization chambers live in that nice, stable saturation region. They don't amplify the signal at all, they just precisely measure the primary charge that was created. And because of that, they are the absolute gold standard for dosimetry and calibration. When you think about the thimble chambers used to calibrate treatment machines, or those long pencil chambers for measuring CTDI, you're thinking about precision.
All right, time for a classic exam question. An ionization chamber operates in which region of that curve? Is it A, B, or C? If you said B, ionization or saturation, you're spot on. That's a core concept you've absolutely got to know.
Okay, this is a fantastic question, and it gets right to the heart of things. You've got these two detectors, both based on gas, but you'd use them for totally different tasks in the clinic. So why is that?
And this is where the analogy is just perfect. An ionization chamber is like a measuring cup. It's built for precision. It tells you exactly how much radiation you have. A Geiger-Müller tube, on the other hand, that's your smoke alarm. It is brilliant at screaming, "Hey, there's radiation here," but it's absolutely terrible at telling you how much. One is for measurement, the other is for detection.
Remember that super high voltage region on the curve? That's where the GM tube lives. A single photon comes in and triggers a massive, complete discharge of the gas. You get a big, easy-to-measure pulse. It's an all-or-nothing event. That's why you get that classic clicking sound for each particle it detects. But, and this is the key part, because every pulse is the same size, it tells you absolutely nothing about the energy of the radiation. And after each click, the tube is effectively dead for a few hundred microseconds while it resets, which means it can get overwhelmed at high count rates.
So let's lock that concept in with another question. Which of these detectors gives you zero information about the energy of the radiation? You got it. It's C, the Geiger-Müller tube. It's a simple counter, and that's it. Okay, let's switch gears and move to our next family of gadgets, scintillators. These work on a totally different and kind of beautiful principle. Instead of collecting ions from a gas, we use a special kind of crystal. When radiation hits the crystal, it deposits energy, and that makes the crystal give off these tiny, tiny flashes of visible light. Our job then is to just count those flashes.
And the most classic example, the one you'll see everywhere, is a sodium iodide crystal doped with a little bit of thallium, that's NaITL. This is the absolute heart of every gamma camera. And why is it so popular? Well, it has a high atomic number, that high Z, so it's really good at stopping gamma rays. It puts out a ton of light for each interaction, which gives us great energy resolution. And that standard 9.5mm thickness, it's pretty much the perfect sweet spot for detecting the 140 keV photons from technetium-99m. Its one major downside, though, is that it's hygroscopic. It loves to suck water out of the air, which would ruin it, so it has to be perfectly sealed up.
Now for PET imaging, we need something totally different. We're detecting those powerful 511 keV photons, and we have to do it incredibly fast. The old school standard was BGO. It's dense, which is great, but man, it is slow. We're talking 300 nanoseconds for that flash of light to fade. The modern standard is LSO or LYSO. And just look at that decay time, 40 nanoseconds. It is ridiculously fast. And that incredible speed is what makes modern time-of-flight PET possible. It's a simple story. Speed wins.
So, the exam question here is a gimme. What's the main advantage of LSL over BGO? You know it. It's C. That much faster scintillation decay is the key technological leap that really unlocked the power of time-of-flight PET. All right, on to our final family of detectors, the really high-tech option. It turns out that the same fundamental material inside your phone and computer chips, silicon, can be used to detect radiation. This is where detector physics gets incredibly precise.
So why are they so much better? It all comes down to this one crucial point. Remember how in a gas detector, it takes about 34 electron volts of energy to create one ion pair? Well, in a silicon semiconductor, it only takes about 3.6 eV to create what's called an electron hole pair. So for the exact same amount of radiation energy deposited, you get roughly 10 times more charge carriers. And more charge carriers just means better statistics, which translates to fantastically better energy resolution.
And this incredible precision is what's driving the next big revolution in CT. These new photon-counting CT scanners, they don't use scintillators, they use semiconductor detectors made of cadmium zinc telluride, or CZT. Each and every X-ray photon gets converted directly into an electrical signal, and its energy is measured on the spot. This totally eliminates a major source of electronic noise, it lets us sort the photons by their energy, which is spectral imaging, and it allows for much smaller pixels for higher resolution. And this isn't science fiction, this technology is in hospitals right now.
Quick check on that. The material making this new technology possible is C, cadmium telluride or cadmium zinc telluride. This is a really key piece of modern imaging physics you'll want to remember.
Okay, so we've met the whole gang of gadgets. We've got the gas detectors, the scintillators, and the semiconductors. So now let's put it all together and figure out which one you would actually grab for some common clinical tasks.
Think of this as your clinical cheat sheet. Need to calibrate a beam? You have to use a thimble ionization chamber for its precision and reproducibility. See a spill and need to check for contamination? You grab that GM tube for its sensitivity and that helpful audible click. Doing standard nuclear medicine imaging, the great light output and high efficiency of NaITL is your go-to. For a modern PET scanner, it's all about the fast timing of LSO for time of flight. And for that cutting-edge spectral CT, it's the direct conversion of CZT that makes it all happen.
Okay, let's nail this down with a super fast 60-second recap. Ready? Go. There are three fundamental mechanisms: ionization in gas, scintillation in crystals, and ionization in semiconductors. Gas detectors are all about the voltage. The stable saturation region is for ionization chambers, perfect for precise dosimetry. The super high voltage region is for Geiger-Müller tubes, great for finding contamination but with no energy info. Scintillators turn radiation into light. NaITL is the workhorse for gamma cameras, while the blindingly fast LSO enables time-of-flight PET. And finally, semiconductors have the best energy resolution, which is the secret sauce behind photon-counting CT using CZT detectors. The most important thing? Always match the right tool to the right job.
This was Lecture 3 of the RadSound Basic Radiation Physics Masterclass. See you in the next one.